So I'm continuing on with the Unit 1 packet, page 29, looking at the limit of a vector valued function. Example 2, calculate the limit for the function, and it's a pretty beefy function, but as t approaches 2. So similar to number 1, what we're going to do is evaluate this function for when t is equal, negative 2, for when t is equal to negative 2. All right, so limit as t approaches negative 2 of r of t. I'm going to replace each t, so all these little t's here, with a negative 2. All right, so I'd be looking at a radical, and it's going to be 4 plus 6 minus 1. We'll simplify in a minute. I plus 4 times negative 2 is negative 8, plus 3 j plus the sine of negative 2 plus 1, negative 1 pi over 2. And that's all of that k. So when we go to simplify here, the coefficient of I, that's simple. 10 minus 1, 9, under the radical is going to give you a 3. I minus 5j. And then the sine of negative pi over 2 is going to be negative 1, so minus k. So it actually simplifies up very nicely. Number 3, we're given a vector value function in 2 dimensions. They're asking us to evaluate, or at least find the limit, when t is equal to negative 3. So it's pretty easy. Negative 3 goes in for t. When I square it, I get a 9, plus 1 is 10. All right, so we're looking at the vector negative 3, 10. Now, slight difference in concept here. It's saying to evaluate the vector valued function when t is equal to negative 3. Right? So the limit is what is the vector valued function approaching. So what are all those vectors approaching as t is moving into negative 3 from negative infinity and also from positive infinity? So what is it zeroing in on? But an evaluation is just simply saying, well, what is the location of the vector when the t value is equal to negative 3. Now in this context, there's no difference because this is a continuous differentiable function because of the 2 components. The 2 components are both everywhere continuous, so you get the linear component for x, or the x component, and the y component is quadratic. Both of them are everywhere continuous, so there won't be a difference between those 2 outcomes. And so this is really just kind of illustrating the fact that if the limit as t is approaching some constant is the same as the evaluated function when t is equal to that constant, then the function is continuous at that location. Right? So is it continuous at t equals negative 3? The answer there would be yes. All right, now D is saying we have the limit as delta t approaches 0. What is the limit of this entire function? And this is a difference quotient. All right, so r of t plus delta t. Right, so we're looking at, really it's still a vector valued function, so we would be looking at this as something that you would evaluate. But I could make my substitution limit as delta t approaches 0. R of t plus delta t would be t plus delta t, because we're popping it in for the t's in each part of the vector valued function. So t plus delta t, and then t plus delta t squared plus 1 minus t comma t squared plus 1, poor quality plus sign, all over the delta t. All right, a little distributive property here. So limit as delta t approaches 0 of t plus delta t, comma, t squared plus 2t delta t plus delta t squared plus the one that's already there, right, and subtracting from that t comma t squared plus 1 all over the delta t. That's going to clean up a little bit anyway to the limit as delta t approaches 0 of, subtract your corresponding components, and we'd be looking at delta t, comma, and the only thing that would cancel in the second part would be, well, actually nothing would cancel in the second part because it doesn't look like we have a, oh no, apologies. We would cancel, I was looking at the wrong thing, we would cancel a t squared and a 1. Alright, so 2t delta t plus delta t squared. Alright, so let me just smidge all this stuff over a little bit, fit it all in, close the bracket, over delta t. So this would be the limit as delta t approaches 0 of 1, because really the same as distributing through with the scalar 1 over delta t, which simplifies down to 1 comma 2t plus delta t. So we're dividing each term by delta t essentially, and when we apply the limit we get 1 comma 2t. And what this is, because we're looking at a difference quotient, is it's showing us the derivative of the vector valued function r of t is the derivative of each component of r of t. All right, so this would actually give us r prime of t. All right. So in number 4, evaluating the function, so same idea, it starts off the same way. I'm replacing all of my t's. Well, first I'm evaluating to make sure that this is a continuous differentiable function. Now, the natural log part of it kind of throws a little wrench into this whole thing, but we would need, because natural logs cannot be, you can't take a log of 0, you can take a log of a negative number, so the t, whatever t is, has to be greater than 0. All right, so I make a little note of that. All right, so just keep that in the back of my mind. Now, pi over 4 is definitely greater than 0, so I'm not concerned about that. Now, exponential e to the t power, and the sign of t are everywhere continuous. All right, they exist from negative infinity to infinity. The restriction comes with the natural log, but where log exists, it is continuous. All right, so when I apply this limit, I'm really just substituting in a pi over 4 everywhere I have a t. All right, so pi over 4i plus the sine of pi over 4, which is radical 2 over 2, j, plus the natural log of pi over 4. No need for an absolute value symbol because it's already positive. We don't have to worry about that. And evaluating the function, because we thought about it critically and arrived at the idea that it was going to be continuous, so I know that what I get for r of pi over 4 is going to be exactly the same. So I just do a little copy paste there, jot that down, throw a big old yes right in here, and then you get to the beef of the problem, which is part D, where we find the derivative, if I can speak. So I'm going to do all that stuff again. It can be a little daunting when it comes to other types of functions, transcendental functions. So you know, you just got to kind of buckle up and dive in. But if you recognize that this is the same as saying r prime of t, then instead of evaluating it by hand, which I'll actually show in a separate video, instead of evaluating it by hand, we could jump right to our solution vector, which would be, and I'll do it in component form, e to the t, sine goes to cosine, natural log of t is 1 over t. Alright, so instead of doing all this stuff here, you could jump right to it, but only because we made the realization that this notation here is implying a derivative, a first derivative.